Today we're going to take a look at counterexamples. So we've seen two proof techniques. We've seen direct proofs and contrapositive proofs, both for a statement that's basically a for all elements in a set. Then we've got some statement. So for example, this might read something like for every x in S, then R of x. So we haven't talked about what if the result that we're trying to prove is actually false. Now, if we think back to our logic time, we know that the negation of a universal quantifier is the existential quantifier, and then putting a not with the statement that we had. So to say not for all x in S, R of x, that's the logical equivalent to saying there exists an x in S such that not R of x. So to prove a statement wrong, what we're doing is we're coming up with what's called a counterexample. So we're finding that element x in the set such that the statement that the result is not true. So we're going to take a look at a few examples of this playing out. So we've got a statement, all right, x in the real numbers, so all of the x's in the real numbers, any real number. Then we've got x squared minus 1, that quantity squared is greater than 0. And in your head, you're probably going, no, it's not, because I could have 0 squared and 0 squared is 0. So hopefully, like, your gut goes, no, it's not true. So if that happens, then you should look at it and you should say, all right, well, I have an example. What if I put in 1? Well, 1 squared is 1. I subtract 1 from that, I have 0. It's squared. 0 squared, 0. It's not greater than 0. So what you found when you do that is a counterexample. All right? So x equals 1 is a counterexample for this statement. Now, anytime that you find a counterexample or in another way prove that a result is false in some kind of way, some statement is false, what you've done is you've disproved the statement. All right? So where examples were not okay to prove the statements that were like for every, all right, or for all, the universally quantified things, existential quantified statements, like the negations of these for all statements, one example is all it takes to disprove it. So let's take a look at this example. We're going to try and disprove the statement that if x is in the integers, so any integer x, then we've got x squared plus x is divided by x squared minus 1 is going to equal x plus 1 divided by x minus 1. Now, in your head, you might be going, this isn't true, or you might be thinking, well, maybe it is. It's okay either way, all right? This is why when you're trying to come up with a proof for something, I suggest throwing a few numbers in, even though the examples that you create are not going to be your proof. They can't be your proof because they're not general. It gives you a feeling for how things work. So with this one, we might try a few examples. And one of the examples you might think to try is, well, let me see if x equals 0 works. So you'd plug in 0, and on the left-hand side of that equal sign, you'd end up with 0 in the numerator and 0 in the denominator. Well, that's not defined. So then we have, on the right-hand side, a 1 in our numerator and a negative 1 in our denominator. Well, that's negative 1. So I have something on the left-hand side that's not defined, something on the right-hand side that is defined as negative 1. So clearly those two are not equal. So in potentially working through some examples to see how this works, you may have actually discovered a counterexample for the result. And that's what we will have done in trying 0. So we instead say we've disproved the statement with x equals 0 as a counterexample. So here's another example. I have a statement that n is an integer if 4 divides n squared minus 1, then 4 divides n minus 1. Again, you might be thinking, hey, like this is not clear to me, or it's super clear to me. Doesn't matter where you fall on it. You plug in some numbers, you give it a try, and you see. So again, trying n equals 3. I'll have 3 squared minus 1. Well, that's 9 minus 1, or 8. So 4 does divide 8. So my P statement, if 4 divides 8, is true. Then 4 divides 3 minus 1 is 2. So 4 divides 2. That's not true. So n equals 3 is a counterexample for this. And here's another example we're going to go through. So for positive integers a, b, and c, I have a to the b to the c equals the quantity a to the b raised to the c power. Now, this is actually a super common mistake in order of operations that people make. When we see a to the b to the c, a lot of people will take a to the b first and then raise it to the c power. That's not actually what you should be doing. You should be simplifying the exponent before you raise things to powers. So you should be taking b to the c and then a to the b to the c. So let's take a look with that in mind and see why these two things are different. So let's consider an example of a being 2, b being 2, and c being 3. Now, when you're trying to decide where to start with counterexamples, I highly encourage you to take a look at the structure you're working with. So we know that if we use 0 as something that we're raising to a power, or 0 as a power, or 1, that those things behave differently than other numbers. So 2 is actually a minimum number that I'd like to use here. And if I use all 2's, then my a, b, and c are actually indistinguishable. So I need to have at least one of them be different than a 2. So that's why we've thrown c equals 3 in here. So if we do this, a to the b to the c is going to be 2 to the 2 to the 3. So 2 to the third power, 2 cubed, is 8. So this is really 2 to the 8th power, which is 256. Now, if instead we have the quantity a to the b and then raise it to the c power, a to the b is going to be 2 squared, 2 to the second power, or 4, and then we'll be raising it to the third power, to the c power. So 4 raised to the third power is actually 64. So we can see that these two are not actually equal to one another. So therefore, we've shown through a counterexample of a equals 2, b equals 2, and c equals 3, that these two statements, a to the b to the c, and the quantity a to the b to the c power, are not actually equal to one another.